Hello guys. In today's video, we'll be talking about basics of data center power. This is a simple video to explain some basic concepts such as like voltages, amps, power, what is real power, what is usable power, what's a watt, what's a volt ampere, what's a volt ampere reactive. I'll talk about those and explain some examples, and I'll be talking about sure circuit breakers and at the end. And obviously, I'll put the videos I used as resources in the description so you can check them out for yourself. And before I spend much more time, let's already get started. The big three. The three primary components of a data center are space, power, and cooling. Obviously, we'll be talking about the power part more in this video, but space and cooling obviously matter because how much space you use, but how much space you use, and cooling already spends so much of your energy that it is basically the purpose of the place is to cool it down because you have so many servers that produce so much heat. The cooling is the main idea that we'll be tagging along with. Power basics, the garden hose analogy. Uh, I assume anyone who's watching this video already knows how electricity basically works, but if not, we'll explain it in this simple way. And this is a really general analogy, like you could see a lot of people using it, so it'll be fine to use it. Voltage, equivalent to pressure. It is the force of electricity flowing through a circuit. How the water would be pressurized inside that hose would be equal to what voltage is, how much pressure there is inside it. Amps, equivalent to flow. It measures the amount of current flowing. How much water is coming out would be how much water is coming out will be the ampere. How much water that is currently passing through the hose, and let's say this is a small hole, right? Normally it goes out like this, and if I make it a little bit smaller, the hole will make it a lot faster in a sense that you will understand the ampere would be higher, therefore there will be more flow. Ohms, equivalent to impedance or resistance, like a king in the house. Apparent power, calculated as volts x amps. This is the potential power available. This is how much water that can come out from this hole in the sense, but let's say I'm only like making out this much is coming out, right? Let's say instead of see like this. See, if all of it were to be used, that would be the apparent power we have. And what that basically means is the potential, the highest water flow that we can achieve. But obviously, this never happens. Real power, the amount of power actually used to do work, like I said, this is the real amount. This is the apparent power. This one doesn't happen, but this one does. This is the amount of water that we would actually get. Think of it like apparent power is the water that is coming to your hose, but let's say your hose has a little pressurizer on the other side and you have to fill it up with water for it to work. And you have to fill up that other one, and that will always be filling up. So you don't actually get this much water. You get this much, and the other one is spent on something else. In a basic manner, this is what electricity would equal to in a car in the I would say do because this is a prime example of what how we explain electricity, the garden hose analogy. AC versus DC power, alternating current. The direction of the current reverses back and forth cynically. Frequency measured in hertz. The US standard is 60 hertz. Europe and Asia is typically 50 hertz. Used for most data center distribution because it is more efficient to transmit over distances. The current flows in only one direction. Sorry, direct current flows in only one direction. Example being batteries, often used in telecom facilities but less common in general data centers due to expensive wiring and resistive losses over distance. Alternating current is basically, let's say the current, let's say you have a power source in a circle motion, and this is the wiring system you have. In this wiring system, you would say, I have this wire and it's gonna pass through, let's say like this, in a general manner. The power would come like this. There's an there's a light bulb here, and the light bulb shines. It comes back. it comes back, right? It's in a motion. But in an alternating current, this is obviously happening 50 times per second. That's what hertz mean. That's how it works. Hertz is how fast it's moving. Basically, that's how we explain it. One divided by the amount of time that's passing, that would equal to hertz. And we say 50 hertz mean this is happening 50 times in a second. So I am changing current which way it is flowing. See, like this 50 times per second. And this is used because it's more efficient to transmit over distances. This is a big deal of it because of how AC behaves. This will be a little bit detailed, but because of how AC behaves, it moves over the current outside the cable that you're using, therefore making it more efficient to use to transmit over long distances. And at one point, it becomes better to use direct current, but that would be more expensive. So we just prefer alternating current AC to transmit this. Current flows in only one direction, like we talked about it already. Often used in telecom facilities, but less common in general. Thus, due to expanded wiring and resistor losses over distance. If it were to be a close distance, then sure, it could be feasible, but with how big the data center is just almost never feasible. Let's continue. Transmission and transformers, the relation between volts and amps. There's an inverse relationship. Raising voltage allows you to lower amperage for the same amount of power. Benefit, lower amperage allows for smaller, less expensive wires. Transformers. Step up transformer increases voltage, lowers amp. Step down transformer decreases voltage, increases amps. The, if you don't know what this means, this is talking about how transformers actually work. Transformers are used to carry over the voltage and amperage we want. And let's say you want lower amp but a higher voltage, so the potential is high. You use a step-up transformator. It increases the voltage and lowers the amp you need. Sorry, not you need the amp you use. You go with 5 amp, you come out with 10 amp, and let's say you were going inside with 10 voltage. Sorry, let's say you were using 10 amps, you come out as 5, and you had 100 voltage, and that 100 voltage becomes 200 instead, and 200 multiplied by 5, 1,000, and on the other side 100 multiplied by 10, that is also the same amount of power. And with this, you can basically see that the amount of power doesn't change, so we are not actually making power out of nothing, right? Obviously, thermodynamics already determined that we cannot do that, but hey, another proof for that. Why not? And basically, we use these to like you usually carry higher voltage and lower amperage through a long series of cables. If a cable is really long, you would do that. And when you go down and when you are at like let's say a neighborhood, you lower the voltage so people can actually use it instead of frying your phone or something like that. So this is how it's basically is moving around. Sorry. Let's continue along. Single phase versus three phase wire. Single phase typically found in residential settings, one or two hot wires. The sine wave crosses zero multiple times. Three phase uses the three conductors with sine waves offset by 20 degrees. Why use it? It's more economical and requires smaller wire size to deliver the same amount of power compared to single phase. Uh, See, if you were to use a single line that is just going along like this, you would have a single phase, but you put three wires, and all of these are 120 degrees different from each other. Let's say like this, one, two, three. All of these are offset by 220 degrees, and you do this so they're not actually crossing each other, and they don't just like boom out of it. They don't go like really high off it. Obviously, they are already different wires, but you do this to use it more efficiently. Of course, smaller wire size to deliver the same amount of power. Like we said, because you're using three phases, you're delivering more power over the line. And we use three phase to carry over all of the power to the data centers. We use three phase to transmit power, not power, voltage through the lines in real life as well. That we transmit electricity with three phase usually, and we turn it into single phase when it's going inside your home. Power factor and some calculations. Power factor, and like I said, remember the analogy I said, this is your power potential, like this is how much water that can come on, but this much comes on. This is why it is. Power factor, the ratio of real power divided by apparent power. Uh, you did, let's say you have 1,000 watts, and you have 800 watts, and you have 1,000 volt amperes. You divide them by each other, you get 0.8, for example, and you use this power factor to calculate how much real, actual usable power you get out of it. Uh, Obviously, if you were using a transformer, an engine, or anything, literally, it would always give you the apparent power on its back on the manual or anything else. It would give you like this is 10 kilovolt amperes, and you would look at the power factor, let's say 0.75. You multiply 10 by 0.75, you get 7,300, and this is your real power. This is why it's important. In a sense, you don't need to know why it's working this way, but obviously you should, because why not? The other 2,700s, I guess you could say volt ampere reactive. And we call it reactive because it's the power that is wasted on other stuff such as, or let's say a capacitor or a bobbin, or I guess you would call it coil for easier English. If you're using those, and obviously you are because these systems require those to use, and other stuff as well that can change the power factor. This obviously makes it so that the power factor is not actually one, and like it says, it represents efficiency from 0 to 1 scale. You obviously want to use the kilowatt because this is what actually moves stuff around. This is what actually does work in a sense that, in a physical sense, or in literally the physics sense, that this is what actually makes work, and the other one is we don't use it. Calculating watts, single phase watts equals volts, amps, power factor, three phase volts, amps, power factor, 1.73. And 1.73 is the square root of 3 derived from the 120-degree phase separation. This is because it's actually symmetrical to use this. Let's say you're in a star shaped, and that star shape would be something like this. Let me see if I can actually make it. And this derives from the 120-degree angle, and I was trying to show it in a sense that you would do a middle triangle separating from each other, and they would a circle, and you put a perimeter, and the perimeter divides them 120 degrees equally to three parts. And this half diameter, you would sorry, this half diameter that you would be the radius. This would work in a way that the symmetry shows it that these powers, the power equals the square root because of the symmetry. This is basically it. It comes from 120 degrees. Cosine, sinus, that's where it comes from. Grounding purpose, a safety measure designed to protect people from electrical shock. Path of least resistance. Electricity always seeks the easiest path to ground. If a loose wire touches a metal case, the case becomes dangerous. Uh, Grounding is basically meaning that electricity would rather go through a lower ohm. Let's say your body has a resistance of 1,000 ohms, and uh, electricity would rather choose 20 ohms than that. And you obviously get a lot less ampere going through your body than the 20 ohms. Because in that way, electricity chooses to prefers to go over the easy routes. You get less amplitude. This is how you would basically live. If a loose wire touches a metal case, the case becomes dangerous because the case doesn't have any way to drop all of this potential energy it has on it, all of the voltage. So the case becomes dangerous because it can pass through you and to the ground in that way. A ground wire provides low resistance path for electricity, bypass a person, and go safely to ground. And this is how it works. Power usage in data center. This is a small graphic that I took from the videos as the research I was using. UPS inefficiency, battery charging, lightning, critical loads, cooling. You can see the percentage they all use, and you can see the cooling is 50%. Sorry. This proves how much, like, actually anything else compared to that, you just use cooling. This is basically how it works. This is a data center power calculation project. This is a small example that I want to show to you guys. Scenario, facility size, equipment, cooling strategy, 50% chill water, 50% direct expansion, base critical load, calculate the power required for IT equipment currently planned 1.5 kilowatts per rack. Calculation, 150 racks, 1.5 kilowatt per rack, 225 kilowatts for all of them. 2. Future load allowance growth. Add a buffer 20% for data center growth, such as adding more servers later. You're adding more servers, you're adding more, let's say, lightning. It doesn't have to be actual servers. It can be anything. You just added another room and you have more fucking you have more Ankim workers. That actually sounded like a swear word. I'm sorry. I didn't think of that. I'm sorry. That you can have more Ankin workers and future load allowance. Like I said, the 20% is all of that. Calculation: 225 multiplied by 0.25, 45 kilowatts. You added that and you get 270 kilowatts. Peak power multiplier. Add overhaul 5% for times of maximum activity. Whole day rush, such and such. This basically means when, let's say, there's a grand prize going on and everyone wants to join a easy sale. Everyone wants to get all of that free money going through them. Everyone wants to join the competition to get the grand prize. Let's say the sorry, everyone wants to join the grand lotto, and why not? Everyone joins it, and it's all saving their names, their informations, getting their money, calculating all of that. You add another 5% for that, the peak maximum calculations. You get 273.5. UPS and battery overhead. This is actually one of the more important parts. Account for power loss to UPS inefficiency and power battery charging, estimating at 32% of the load. Uh, you would say the inefficiency is, let's say, like 12%, and the battery charging usually costs around 20% of the power that it actually has. Of the whole entire thing, it will cost 20% of that. And through that, you would calculate how much more energy is going to go through that. And 10% is the inefficiency of the UPS because nothing can actually transfer energy at 100% efficiency rate. So you get the new rate of a 86.5. This is the other load. Lightning load. Estimate lightning needs based on square footage, 2 watts per square foot. Obviously, you need to light the place so people can actually do stuff. And you do that with 2 watts per square foot. Calculation: 5,000 square feet multiplied by 2 watts, 10 kilowatts. Total infrastructure load, pre-cooling. Sum of all non-cooling loads calculated above: 270, 13, 26, to 380 kilowatts. Cooling load, Calculate the power needed to cool 380 kilowatts infrastructure load. The load is split evenly between two cooling types, 190 kilowatts each. Chilled water, efficient, and you say efficient and you add a factor because it doesn't have to be like that. You use the factor and it says 133 kilowatts. This is how much energy used to chill down the servers with chilled water. Direct expansion, less efficient, 190 multiplied by one factor because it's less efficient. Total cooling power, like it says, 323 kilowatts. Total facility power requirement, sum of all of it, 703. Utility request. NIC complement. National Electric Code usually requires that you do not exceed 80% of circuit capacity. Therefore, you must request 125% of your total need. Calculation, you put all of this so you don't actually go overboard and destroy everything. Generator sizing. Generators are sized differently for IT loads. Generators are used when power goes out. You immediately start using them until the UPS runs out. Well, not the UPS doesn't run out, but until the generators start moving, they start rolling so they can actually produce electricity. Use the UPS, then you move on to the generators. Infrastructure portion, 280, 1.3, 494. Cooling portion, another 1.55 multiplier. Total generator size, 195 kilowatts. This is needed because there might be stuff that you don't know that might happen. The UPS, the such fails, or some of it fails, so you need to actually supply more power. For some reason your efficiency went down because you don't know the power went out. Something might have broken, so you're less efficiently working now. So you might use more power. This is why it matters that you use actually bigger generators than what you need. And in this one, I'll explain what circuit breakers are basically with some pictures so that it's not complicated for people to understand. Sorry. Let me continue. I'll be talking about circuit breakers. This power distribution unit provides this much energy, this much whatever. And so, what is what is a circuit breaker? A circuit breaker basically is the component that actually cuts energy when the limitations are passed or they are bypassed through like the overflow, or if there's a thermal problem. There might be a lot of problems, but it's usually about amperage. So in this example, you're seeing that the power distribution unit has a 50 amps. It says 50 amps here, it says 30 amps, and then it says 20 amps here. 50 amps means there's a circuit breaker that requires 50 amps to be activated so that it cuts the energy to this all of these servers. And you see 30 amps here, and if it goes above 30 amps, it's gonna close off all of these servers so that they cannot get energy. And it says 20 amps here. The servers need 20. The servers have 20 amp circuit breakers. And why is that? The server was pulling 25 amperes, and see the deal. We have a 20 amp circuit breaker. So the deal is the server will go off. And why is that? Because you're pulling 25 amps. It's above the circuit breaker limit. So what is the circuit breaker going to do? It's going to open itself so the server doesn't fry because you're sending too much amps to the server, and it's going to fry itself. And you should be planning that you put 20 amps on all of these servers, and you don't put 20 amps right here on the power distribution unit where the 50 amps is, because if you go like 25 amps and you put 50 amps circuit breaker here, then it's gonna just it's gonna open the circuit breaker right here at 20 amps, and all of the servers will be turned off. But if you just do it here, only this server has a problem. The other servers can still work. So you won't be losing as much as money. You won't be losing benefits. You won't be losing all of that energy going into nowhere. So you put the lower amps through the thing that you're actually trying to protect. And other power distribution unit would get the higher amp circuit breaker because obviously it's going to provide more energy, so it's going to have more amps. So you put all of them individually at that amp, and if one fails, the other one can still continue working. Causes of power system failure. Well, let me do it like this. PDU and associated circuit breakers, 30%. All other circuit breakers, 40%. UPS and other causes, 30%. As you can see here, circuit breakers are only 70% of all power system failures. This is a huge margin. And the reason why it's like this is the bad planning of the circuit breakers causes for this to happen. Like I said, if you were to put 20 amps here and all of these servers go off, then obviously it's going to contribute to power system failure in all of them. So this is about how bad or good you plan, where you need to put the circuit breakers, what their limitations are, how they work and such. This is obviously dependent on who's designing the circuit breaker mapping and where they should be put and such. Magnetic circuit breaker, short circuit protection. Get closer so you can see. Spring force keeps contacts closed. Electromagnetic coil forces contacts open. If there was a lot of amps going through this, the coil would see, and the coil wouldn't see. The coil would know that a lot of amps is going through it. So magnetically speaking, it would be charged. So the spring itself opens itself. Why does this happen? Because it's an electromagnet, actually. This is what the coil is used for. If a lot of amps are going through it, it opens itself, and it's a short circuit protection. During short circuits, so much amp goes through it. Let's say it says 20 amps here. It might be, let's say, 4,000 amps. It might be around maybe 8,000 amps passing through a single line. Obviously, at a server that would be a lot lower than that. Maybe like 1K amps, 2K amps, something around that. But the idea is it can be up to 2,000 times of the value that is on the circuit breaker, and it needs to hold on to this because if it fries, it's going to let more of the amps pass through before it burn itself, and we don't want stuff to burn because it's going to turn into a big fire. We don't want that to happen. And we don't want our circuit breaker to break either, because not circuit breaker to burn either. Or if it burns, it's just gonna fry the server as well. Even if it doesn't burn the entire place, it's gonna do that. So you need to open it. You need to act before that happens, so you don't actually start a fire. And this is how a magnetic one works. Circuit breaker sizing. 22 amps, 20 amps, 16 amps, what do they mean? 100 to 10% of the rating allows for short-term overloads. It says that I would open at 22 amps if I am rated at 20 amps. It's a circuit breaker. If it's at 20 amps, I'm gonna open at 22 amps because sometimes it might be like a little bit higher for a while because there's a lot more let's say sorry, there's a lot more wanting of that energy to be used. There's a lot more usage going on at that moment, power usage going on at that moment. So you use instead of, let's say, 15 amps, you're using 19 amps so that it doesn't open itself when it hits 20 amp immediately. 16 amps, 80% of rating threshold for continuous loads. It says that if your circuit breaker is 20 amps, or you would be choosing this based on how much amps that is passing through your cable. Let's say you have 20 amps passing through, so you would make it so that it's higher 20%. What is 20% of 20? It's 25. So you would say I want a circuit breaker that is 25 amps, and my 80% rating means I am always using at least 20 amps going through that cable so that it doesn't open itself. This is a limitation for that. And this is basically it on how they should be working, what you should be doing. And let me see. What you should be basically doing with circuit breakers, how power management works. I talked about simple concept this time, but obviously we'll be going into deep territory a lot more, and in the next videos we'll be doing that. Thanks for watching, and if you're confused about anything, you can comment down below, and I will try to explain to my best ability, to my ability to be best ability. Anyway, I'm kidding. Obviously, I'll try my best to help you out, and you can always, obviously, just ask me. I'll put the resources down, and I'll see you later next time.